Black holes are proven. Photographs exist. Gravitational waves have been detected, and every collision confirms the same answer. But all of that evidence, every shadow, every pulse, every ring of warped light shows the outside. Nobody has measured the inside. The center, the place where density hits infinity and volume drops to zero, is a prediction that produces an absurd result. For 100 years, that failure was treated as a feature, not a flaw. Now, the same equations allow a completely different object in the same place. A frozen shell around a core of repulsive energy. No pit at the center, no point of no return, and no broken physics. The difference between the two objects is smaller than an atom, scaled down by a factor so extreme that no instrument can resolve the gap, and nobody can prove which one is real. That gap between two answers is not a gap in the data. The gap is a crack in a deeper assumption. The universe owes us a single answer for every question we ask. For a century, the math behind collapsed stars has carried a confession. The equations work perfectly on the outside. The equations produce nonsense on the inside, and the object that fixes the nonsense connects dead stars to a force far worse. Cosmic expansion, pulling every galaxy away from every other galaxy right now, faster every year, not a correction, a fuse. Every new gravitational wave detection lands in the silence between two realities. Nobody alive can separate the two, and the question is no longer which object is real. The question is, what happens to physics if the answer never arrives? This video is one entry in a much larger series. If you want to see where the rest goes, hit that like button and subscribe so you do not miss what comes next in this story. Black holes are proven, or so the story goes. Every observation we have ever collected from these objects comes from the outside. The photograph that made headlines around the world in 2019, the glowing ring captured by the Event Horizon Telescope, showed the shadow of a boundary. Not the boundary itself, not the interior. The light that formed that image traveled from superheated gas, swirling at nearly the speed of light, bending around an object so massive that photons curve into orbit. The image was celebrated as proof. But proof of what, exactly? Proof that an object extremely massive, extremely compact, and extremely dark sits at the center of the galaxy, Messier 87. The photograph confirmed, beyond reasonable doubt, that the outside matched the prediction of general relativity. But about the inside, the photograph was completely, absolutely silent, and nobody, in the celebration that followed, paused long enough to say that out loud. 200 researchers across 8 telescopes spanning 4 continents synchronized their observations using atomic clocks. Katie Bowman, a computer scientist at the Massachusetts Institute of Technology, developed the imaging algorithm that stitched the data into a single coherent picture. When the result appeared on screen for the first time, the room went silent. The orange ring, slightly asymmetric, thicker on one side where gas was moving toward the observer, perfectly matched the prediction from general relativity for the exterior geometry of a 6.5 billion solar mass object. Extraordinary, and celebrated around the world as final confirmation. The confirmation of the outside only, and in a way nobody discussed on camera, deeply incomplete. The frame showed the environment around the object, swirling accretion disk, the bent photon paths. Another showed how light curves near the surface. Neither showed anything about what happens past the point where light can no longer escape. That point, the event horizon, is the defining feature of these objects. Cross the horizon from the outside, and no signal, no particle, no whisper of information can ever return. Light bends inward. Time, as measured by a distant observer, slows to a stop. The concept is elegant, terrifying, and foundational to every model the field has built over the last century. Yet the event horizon is also the single most important feature in all of physics that has never been directly observed. No telescope has imaged the horizon. A single probe has crossed the boundary and sent data back. Gravitational wave detectors have never measured the horizon itself, not once. Every claim about the existence of the event horizon is an inference. The reasoning is straightforward. General relativity predicts the horizon. General relativity has passed every test we have thrown at the theory, and therefore the horizon must exist. But straightforward reasoning is not the same as direct evidence, and the gap between the two is wider than most people realize. Philosophers of science would recognize this logic in a heartbeat. A theory predicts a feature, and that theory passes other tests elsewhere. Therefore, the feature is real. But passing other tests is not the same as observing the feature. Not even close. General relativity has been confirmed with extraordinary precision in weak gravitational fields. Clocks on satellites tick at slightly different rates than clocks on the ground, exactly as the theory predicts. Light bends around the sun during a solar eclipse, exactly as Arthur Eddington measured in 1919. The orbit of Mercury precesses at precisely the rate the equations demand. Every one of those tests probes the theory in a regime where gravity is weak and curvature is gentle. The event horizon sits in a regime where gravity is extreme, where curvature is enormous, and where quantum effects might intervene in ways that no weak field test can reveal. Confirming the theory in one regime and assuming the theory holds in a completely different regime is an extrapolation, not a proof. The situation at the center is worse, far worse. General relativity does not merely predict a horizon. The equations predict that all the mass of the collapsed star continues falling inward, past the horizon, through the interior, until the entire mass occupies a single point. Zero volume, infinite density. Physicists gave this outcome a name, singularity. Clinical as the word sounds, what hides behind the label is an admission of pure failure. Infinite density is not a physical state. No laboratory has ever produced infinite density, and no experiment in the history of science has ever measured infinite density. Infinite density is what the equations produce when pushed past the domain where those equations apply. In every other branch of physics, when a calculation returns infinity, the standard interpretation is that the model is incomplete. The model does not describe reality at that scale. A new theory is needed. But in the case of collapsed stars, the field chose a different path. The field gave the infinity a name. The field called the name a prediction. And the field moved forward, treating the prediction as a feature rather than a flaw. Carl Schwarzschild found the first exact solution to the field equations of general relativity in 1916, barely a month after Einstein published the theory. Schwarzschild was not sitting in the university office. Schwarzschild was stationed on the eastern front of World War I, calculating by candlelight between artillery bombardments. The solution described the geometry of empty space around a single spherical mass, and the solution contained two mathematical singularities, one at the center, where the curvature became infinite, one at a specific radius, the distance that would later carry the name Schwarzschild radius, where certain terms in the equations diverged simultaneously. Schwarzschild himself was uncertain what the singularities meant physically. Within months of completing the calculation, Schwarzschild contracted a rare autoimmune disease on the front lines. He died in May of 1916, at the age of 42, never knowing that his solution would define an entirely new class of object and reshape theoretical physics for the next century. For decades after the death of Schwarzschild, physicists debated one question: was the singularity at the Schwarzschild radius physically real, or merely an artifact of the coordinate system? In 1958, David Finkelstein demonstrated a remarkable result. A simple change of coordinates could remove the singularity at the Schwarzschild radius entirely. The surface was not a physical barrier. The surface was a one-way membrane. Anything crossing the membrane from the outside could never return. It itself became trapped past that boundary. And the resolution was also, in a precise mathematical sense, an assumption dressed as a theorem. But the argument from Finkelstein required a critical assumption. The space at and inside the Schwarzschild radius must be completely empty. No matter, no energy, zero phase transitions, zero quantum corrections, pure vacuum all the way down. The mathematics of analytic continuation, the technique used to extend the exterior solution through the horizon and into the interior, demands that the stress energy tensor vanish at the boundary. What happens at the horizon is a choice, not a conclusion. That choice has never been, And so the assumption stood for decades, unquestioned, because questioning the assumption would mean questioning everything built on the assumption. Testing that choice remains beyond any instrument that exists today. Emil Mottola at Los Alamos National Laboratory would later make this point explicit. Mottola had spent years studying the behavior of quantum fields in curved space-time, the branch of physics that sits at the boundary between general relativity and quantum mechanics. Mottola noticed a detail the community had glossed over for decades. When a photon falls towards the Schwarzschild radius, the frequency of the photon, as measured by distant observers, increases without bound. The photon blue shifts toward infinite energy. In classical physics, infinite blue shift is a coordinate effect, removable by switching to the freely falling frame. But in quantum physics, the energy of a photon is a physical quantity. A photon with arbitrarily high energy interacts with the vacuum in ways that cannot be ignored. The effective gravitational coupling grows with energy. At the Planck energy, roughly 10 to the power of 19 billion electron volts, quantum gravitational effects become dominant. And the approach to the Schwarzschild radius drives photon energy toward exactly that scale. The horizon is not a place where nothing happens. The horizon is a place where the classical theory is screaming that a transition must occur. And the classical theory, for all of the power of that theory, does not have the tools to describe what that transition looks like. Roger Penrose proved in 1965 that under very general conditions, once a trapped surface forms during gravitational collapse, a singularity must follow. The proof was a masterpiece of mathematical physics. The proof earned Penrose a share of the 2020 Nobel Prize in Physics more than half a century after the original publication. But the proof was conditional. The proof assumed that the matter inside the collapsing star obeyed certain energy conditions, specifically the null energy condition, which states that the energy density measured by any light-like observer is never negative. Quantum mechanics violates this condition routinely. The Casimir effect, the measurable force between two uncharged metal plates in a vacuum, exists because quantum fluctuations produce negative energy densities between the plates. Hawking radiation, the theoretical prediction that collapsed objects slowly evaporate, also requires violations of the null energy condition near the horizon. The proof from Penrose assumed no exotic phase transition intervened during the collapse. The proof from Penrose assumed the interior remained classical. Every one of those assumptions could be wrong, and if any single assumption fails, the singularity is no longer guaranteed. The embarrassment at the center persisted for a century, not as an unsolved problem that the community was actively trying to fix. Nobody framed the mathematical failure as a question worth pursuing. Nobody treated the breakdown as a puzzle worth solving, or a failure worth confronting, or even a crack worth examining. The embarrassment persisted as a named feature that textbooks presented as settled science. Diagrams depicted the breakdown as a crushing point. Lecture slides labeled the breakdown as a prediction. Popular science books illustrated the collapse with a funnel narrowing to a point, matter crushed into oblivion. Every visual was compelling. Every visual was also a guess, dressed in the authority of a theory that had been confirmed only on the outside. Nobody questioned the image because nobody had an alternative image to offer. The funnel with the point at the bottom was the only picture available, and an only picture becomes the truth by default. Students learned the name. Students drew the diagram. The Penrose diagram, the elegant conformal map showing the entire causal structure of the spacetime, the horizon, the point of infinite density, the regions that can never communicate, became the standard way to visualize what happens inside a collapsed star. Generations of physicists built entire careers on the structure of that diagram. Over decades, the diagram became so familiar, so central to the culture of the field, that questioning the picture felt like questioning gravity itself. But a diagram is not an observation. Every line on that diagram is a consequence of assumptions, and assumptions, no matter how mathematically elegant, are not evidence. Gravitational waves tell the same incomplete story. When two compact objects spiral inward and merge, the signal encodes the masses, the spins, and the exterior geometry. Only the final portion, the ring down, carries information about the structure of the merged remnant, and the ring down is dominated by the quasi-normal mode, the characteristic vibration frequency of the merged remnant, similar to how a bell ring pitch set by the bell's shape. For objects as compact as these, the dominant frequency depends almost entirely on the total mass and the spin. Higher order frequencies, the ones that might distinguish the interior structure, are orders of magnitude fainter. LIGO, the Laser Interferometer Gravitational Wave Observatory, has detected dozens of mergers since the first signal arrived on September 14, 2015. Every merger is consistent with the standard prediction, and every merger is equally consistent with any alternative compact object, one whose exterior geometry is identical regardless of what occupies the interior. Instruments cannot distinguish a bottomless pit from a frozen shell. Detectors measure the outside. Cecilia Cirenti and Luciana Rizzola demonstrated this directly in 2016 when the first gravitational wave detection was still fresh. Cirenti and Rizzola modeled the ring-down signal, the signal a rotating Gravastar would produce after a merger, and compared the result to the signal LIGO actually recorded. The Gravastar model did not match, but the mismatch depended entirely on the specific internal structure assumed. Change the equation of state inside the shell, and the predictions shift. The parameter space of possible interiors remains vast, and a single observation cannot rule out a family of alternatives that spans that space. Every additional detection narrows the range. No detection so far has closed the range to zero. All the evidence that earned Nobel Prizes, all the evidence that landed on front pages, is evidence about the exterior. Nobody has observed the inside. Nobody has tested the inside. And most famous objects in modern physics, the ones printed on t-shirts and painted on murals, rest on a foundation that has never been examined directly. And now the first question arrives, the one that cracks the foundation open. What if the same equations that predict the pit also allow a completely different structure where the pit was supposed to be? The math allows the opposite, not as speculation, not as a thought experiment scribbled in the margins of a notebook, as a published, peer-reviewed solution to the same field equations that predicted the pit in the first place. The same mathematics that produced the singularity, the same framework that generated the event horizon, also produces a completely different object. An object with no singularity and no horizon, no point where physics surrenders. And the exterior of this object, the part that every telescope and every detector can actually measure, is identical. Perfectly, maddeningly identical. Seeds of the idea are older than most physicists realize. In 1966, in the Soviet Union, two physicists working independently arrived at the same radical suggestion. Andrei Sakharov, the nuclear physicist who would later become one of the most famous dissidents of the Cold War, and E.B. Kleiner, a less celebrated theorist, both proposed that the interior of a collapsed star might not contain a singularity at all. Instead, the interior might be filled with repulsive energy, a vacuum state that pushes outward against further compression. Sakharov and Kleiner published in the same Soviet physics journal in the same year, apparently without coordinating. Those proposals sat buried in the literature for decades. Western physicists focused on the Penrose singularity theorems and the golden age of classical general relativity, had little reason to dig through Soviet journals for alternatives to an object the Western community was busy celebrating. Seeds germinated in silence. By the time Western physicists encountered the idea, the original papers were nearly forgotten, and the field had already committed deeply and publicly to the object those papers were meant to replace. 35 years later, the seeds broke ground. Paul Mazur, a physicist at the University of South Carolina, and Emil Mottola, a theorist at Los Alamos National Laboratory, submitted a paper on September 11, 2001. The timing was catastrophic. The world turned toward a different kind of collapse that morning, and the paper landed on the preprint server with almost no attention. Mottola had already recognized that the blue shift near the Schwarzschild radius is more than a mathematical curiosity. Photons falling toward that boundary gain energy without limit and the quantum vacuum cannot ignore photons whose energy climbs toward the Planck scale. A quantum intervention must occur. Mazur and Mottola built a model describing exactly what that intervention produces. The two physicists took the screaming signal from the classical equations and asked what happens when quantum mechanics is allowed to answer. Not a correction to the existing picture, a replacement. According to Mazur and Mottola, the replacement is a phase transition, the same kind of abrupt reorganization that turns water into ice or iron into a magnet. As the collapsing star approaches the Schwarzschild radius, the quantum vacuum undergoes a sudden change of state. Collapse does not finish. Matter does not fall forever. Instead, the falling material freezes into a thin shell of the stiffest substance permitted by the laws of physics, a shell where the speed of sound equals the speed of light. And inside that shell, where the singularity was supposed to be, sits a ball of energy that pushes outward, repulsive energy. The same kind of energy that is right now, at this moment, pulling every galaxy in the observable universe away from every other galaxy. The pair gave the object a name, Gravitational Vacuum Condensate Star, and within months, the community shortened the name. Gravastar. Clinical, almost forgettable, and hiding a fact that should make anyone paying attention deeply uncomfortable. Because the energy sitting inside the frozen layer is not exotic, not hypothetical. That energy is the same force that astronomers confirmed in 1998 when two independent teams discovered that the expansion of the universe is accelerating. Dark energy, responsible for 70% of the total energy budget of the cosmos. The force that will, over billions of years, isolate every galaxy from every other galaxy until the observable universe contains nothing but the local group, surrounded by an expanding wall of silence. That force, according to the pair, is what fills the interior of every collapsed star. Not a pit, not a point of infinite density. A bubble of the most powerful repulsive force in the known universe, trapped inside a prison of ultra-stiff matter. The structure has three regions. The interior is de Sitter spacetime, a geometry first described by Willem de Sitter in 1917, 1 year after Schwarzschild found the solution that would carry the Schwarzschild name. De Sitter spacetime is the geometry of a universe dominated entirely by vacuum energy. Pressure inside this region is negative, not slightly negative, maximally negative. Equal to the negative of the energy density, the pressure reverses every intuition about compression. Push in any direction, and the vacuum pushes back with exactly the same force. Stable geometry. Energy persists without dissipation. The interior sits in a single macroscopic quantum state, a Bose, Einstein condensate of gravitational origin with zero entropy, zero disorder, a single, coherent quantum configuration occupying the entire interior volume. The frozen layer surrounding the interior is thin. For a collapsed star with the mass of the Sun, the layer thickness is approximately 3 × 10 to the -14th centimeters. Absurdly small. Smaller than an atomic nucleus by a factor of roughly 100. But the number is also vastly larger than the Planck length, 10 to the -33rd centimeters, the scale where quantum gravity is expected to dominate. 19 orders of magnitude separate the two scales. Quantum, but not Planckian. Extreme, but not beyond the reach of known frameworks. Inside the stiff crust, the equation of state reaches the limit permitted by causality. Pressure equals the energy density. Sound travels at the speed of light. No material in any laboratory on Earth, in any experiment ever conducted, has achieved this equation of state. Causality permits the condition. General relativity allows the condition, and quantum field theory does as well. The stiff crust is the hardest, densest, most extreme form of matter that the laws of physics permit without violating the laws of physics. A traveler approaching the object would detect nothing unusual until the final fraction of a distance smaller than a proton. The gravitational pull outside feels identical to that of a classical collapsed object. Light bends along the same paths. Clocks slow at the same rate. Only at the surface of the stiff crust, In a region so thin that the region defies measurement, does the difference between the two objects appear. On one side of that impossibly thin transition, the classical prediction says empty space falling forever toward a point of infinite density. On the other side, the frozen layer says the collapse stopped, the stiff crust formed, and the interior filled with the same repulsive energy. The energy that drives the expansion of the cosmos. Two fundamentally different interiors separated by a barrier thinner than any instrument has ever resolved. The pair drew an analogy to the Aharonov-Bohm effect from quantum mechanics. An electron traveling outside a perfectly shielded magnetic solenoid still experiences a measurable phase shift, even when the electromagnetic field at the electron is exactly zero. Quantum objects respond to the potential, not just the field. Applied to gravity, the same logic holds. A classical test particle falling through the Schwarzschild radius feels nothing unusual, but quantum matter, with wave-like properties sensitive to the global structure of the space-time, might respond to the potential in ways that the classical treatment cannot see. Where the classical and quantum descriptions diverge, the quantum description wins. Outside the membrane, the geometry is Schwarzschild. Exactly Schwarzschild. The same solution that Karl Schwarzschild derived more than a century ago. The same curved space-time that bends photons into rings, slows clocks, produces the shadow imaged by the Event Horizon Telescope. Every measurement made from outside this object returns the same answer that every measurement of a classical collapsed object would return. Mass, gravitational pull, bending of light, orbital mechanics, all identical. Cold, dark, and from the outside a perfect twin of the object that every textbook says should be there. The Los Alamos theorist and the South Carolina physicist were not guessing. Their mathematics is exact. Three regions glued together using the Israel junction conditions, a set of rules developed by Werner Israel in 1966 for matching two different space-time geometries across a thin interface. Junction conditions demand that geometry is continuous across each surface. Surface energy and surface pressure must satisfy specific relationships. When the surface energy densities of both interfaces are set to zero, the simplest possible matching, the metric functions are continuous everywhere. No discontinuity anywhere in the continuous geometry of the merged space-time. Not a single singularity. No point of no return. An inner surface exerts an outward force, a negative surface tension produced by the repulsive vacuum. An outer surface exerts an inward force, a positive surface tension produced by gravity. The frozen layer sits confined between these two opposing forces, squeezed from both sides, stable against small perturbations. Mazur and Mottola proved stability using the microcanonical ensemble, showing that the entropy functional is maximized under small fluctuations, no collapse, and no explosion. Only stillness. Entropy is the detail that should have shaken the field awake. A classical collapsed object of one solar mass carries a Bekenstein, Hawking entropy of approximately 10 to the 77th in natural units, almost incomprehensibly large. The total disorder of the entire observable universe, excluding collapsed objects, is roughly 10 to the 88th. A single solar mass collapsed object carries disorder comparable to a meaningful fraction of all other objects combined. That number was celebrated as a triumph, one that connected gravity to thermodynamics, earned Nobel Prize consideration. But the pair pointed out a flaw that the celebration obscured. The Bekenstein-Hawking formula cancels out the Planck constant entirely. A formula supposed to be quantum contains no quantum mechanics, a classical relic dressed in quantum clothing. The pair drew a direct comparison to the ultraviolet catastrophe of 1900, the moment when classical physics predicted that a hot object should radiate infinite energy at short wavelengths. Absurd prediction, yet mathematically correct within the classical framework. The resolution required quantum mechanics, and when Planck introduced quantization, the catastrophe vanished. The comparison was not a polite disagreement. Likening the celebrated Bekenstein-Hawking formula to the Rayleigh-Jeans law, the very error whose correction gave birth to quantum mechanics, was a direct accusation. The accusation implied that an entire generation of theorists had built careers on a formula that works in a limited regime but diverges catastrophically when pushed to the extreme. Gravastar disorder, by contrast, scales as the mass raised to the 3 arbs power. For a solar mass object, roughly 10 to the 57th, 20 orders of magnitude smaller, comparable to the disorder of the star that formed the object in the first place. The response from the field was not outrage. The response was silence. Not the silence of agreement, and not the silence of dismissal. The silence of a community that recognized the argument but could not afford the cost of engaging with the conclusion. If the Bekenstein-Hawking formula truly was the gravitational equivalent of the Rayleigh-Jeans law, then decades of work on black hole thermodynamics, an entire wing of theoretical physics, rested on a formula whose deepest claim was an artifact. That silence would persist for years because addressing the accusation meant confronting the possibility that the most celebrated result in quantum gravity was a mathematical coincidence. No information paradox, no missing information. Gravity and quantum mechanics no longer contradict. Information never disappeared because the point of no return never formed. Generations of theorists had spent careers trying to explain where information goes when matter crosses that barrier. Hawking had bet Preskill that information is destroyed. In 2004, at a conference in Dublin, Hawking stood before an audience of physicists and conceded the bet. The prize was a baseball encyclopedia handed to Preskill while cameras flashed, and the physics community declared the paradox resolved. Susskind, who had argued for decades that information must be preserved, watched from the audience, but the concession was premature. Hawking conceded that information survives because the standard framework preserves the information somehow, through mechanisms involving holographic screens and quantum error-correcting codes. The paradox had consumed thousands of papers, hundreds of conferences, and some of the finest minds in theoretical physics. All of that effort was directed at a problem that only exists if the barrier is real. Remove the barrier, and the scaffolding of the paradox collapses. Information was never trapped, never lost. The question was built on an assumption, and the assumption was never tested. The elaborate proposals, the decades of debate, the bet itself, all addressed a problem that a different object dissolves entirely. But here is the detail that transforms discomfort into unease. The energy sitting inside every Gravastar is not inert. That energy has a cosmological identity. 3 years after the original preprint landed unnoticed on September 11th, the formal version of the proposal reached the proceedings of the National Academy of Sciences. Publication in the proceedings required a member of the Academy to sponsor the submission. The paper had spent 3 years circulating on the preprint server, accumulating citations slowly, drawing skeptics and supporters in roughly equal measure, building a quiet audience among relativists. When the formal publication arrived in 2004, the connection was made explicit for a journal audience that extended far beyond the general relativity community. The de Sitter interior of the alternative object is the same geometry that describes an accelerating universe. Vacuum energy inside the stiff crust is the same vacuum energy that is pulling the cosmos apart. Every collapsed star, if the Gravastar model is correct, contains a pocket of the force that is reshaping the large-scale structure of the universe. The darkest objects in the cosmos are not empty. The darkest objects are full of the most powerful repulsive force known to physics, and that force does not care about confinement. The force pushes outward against the membrane, and the membrane pushes inward against the force, and the equilibrium holds. For now, consider what that equilibrium means for the universe at large. Every collapsed remnant of every massive star that has ever died, every object sitting at the center of every galaxy, every detection that LIGO has recorded, all of those objects might contain a pocket of the same energy responsible for the accelerating expansion. Not passive corpses of dead stars, active reservoirs of the force reshaping the cosmos. The connection between the smallest collapsed objects and the largest force in the universe is not a metaphor. That connection is a direct consequence of the equations, the same equations, an identical framework The same theory of gravity that predicts the pit also predicts the bubble, and no instrument that exists today can distinguish between the two. The difference between the two is concentrated in a region smaller than any detector has ever resolved. The condensate star sits at a radius that differs from the Schwarzschild radius by a tiny offset, roughly equal to the ratio of the Planck mass to the mass of the object. For a solar mass object, that ratio is roughly 10 to the negative 38th. The surface hovers just outside the location where the event horizon would be, separated by a distance so small that the distance makes the diameter of a proton look like the orbit of Jupiter. Photons forming the shadow seen by the Event Horizon Telescope would follow the same paths around a Gravastar as around a classical collapsed object. Gravitational waves produced by two merging condensate stars would match the waves produced by two merging classical objects through the inspiral, through the plunge, through every phase of the merger that current detectors can resolve. Ring of light, orbital decay, mass measurement, all the same. Two fundamentally different objects, one with a center and one without, one with a barrier and one without, one that destroys information and one that preserves information, producing signals so similar that the similarity mocks every instrument ever built to measure the cosmos. The first ring-down test arrived in 2016, shortly after LIGO detected the first gravitational wave signal in human history. Correnti and Rezzola, who had predicted 9 years earlier that gravitational waves would be the tool to break the deadlock, compared the vibration frequencies of rotating Gravastars to the signal that LIGO had recorded. The frequencies occupied different regions of parameter space. For the specific model tested, the signal matched the classical prediction, not the frozen bubble. That result should have closed the case. But the mismatch depended on the specific model of the stiff crust. Change the internal structure, adjust the equation of state, allow anisotropic pressure, and the vibration frequency shift. Possible Gravastar configurations span a multi-dimensional range, and no single measurement can exclude the full set of alternatives populating that range. Each new detection constrains the range further. No detection so far has reduced the range to 0. The inspiral is blind. The ring down is suggestive, and the gap between suggestive and conclusive is where two realities continue to coexist. Identical from the outside, opposite on the inside, separated by a distance smaller than the smallest distance anyone has ever measured. If nobody can tell the difference from the outside, the question becomes, what about the evidence that should not exist at all? Data should settle the question once and for all. Two objects that look identical from the outside but are opposites on the inside, that situation cannot survive contact with real measurements. Somewhere in the universe, a collision is happening right now. Two compact remnants, each carrying the mass of dozens of dead stars, are spiraling toward one another, accelerating through the final orbits. The energy radiates outward as gravitational waves, traveling at the speed of light across the expanding cosmos. And somewhere on Earth, a detector is waiting. When the signal arrives, the deadlock should break. Which of the two interiors is real should finally, decisively, become clear. For the first time in this debate, that signal has arrived. Not once, but 3 separate times. And yet, the signal settled absolutely nothing. Instead of breaking through, every single detection only deepened the silence further. On September 14, 2015, at 5:51 in the morning, Eastern Daylight Time, the twin detectors of LIGO, one in Livingston, Louisiana, and one in Hanford, Washington, separated by 3,000 kilometers of the continental United States, recorded a simultaneous disturbance. The disturbance lasted less than a quarter of a second. The pattern was unmistakable. A chirp, rising in frequency and amplitude, exactly the signature predicted by general relativity for two massive compact objects spiraling inward, colliding, and merging into a single remnant. The event carried the designation GW150914. Two objects, roughly 36 and 29 solar masses, had spiraled together and merged roughly 1.3 billion light-years from Earth. Energy released during the final fraction of a second exceeded the combined light output, of every star in the observable universe. For that brief instant, the collision was the most powerful event in the cosmos. LIGO and Virgo published with a confidence level exceeding 5 standard deviations, the gold standard threshold in experimental physics. A 1 in 3.5 million chance of arising from random noise. Front pages around the world carried the story. A century after Einstein predicted gravitational waves, humans had finally detected the ripple in the fabric of space-time. The detection earned the 2017 Nobel Prize in Physics, awarded to Rainer Weiss of the Massachusetts Institute of Technology, Kip Thorne of the California Institute of Technology, and Barry Barish, also of Caltech. Nobody disputed the signal. Nobody disputed the merger itself or the staggering energy of the collision. But the celebration obscured a critical silence. The signal confirmed the outside. The inspiral, the plunge, the radiated energy, the total mass, the final spin, all consistent with the exterior geometry of two extremely massive, extremely compact objects spiraling together and producing a merged remnant. Every number matched. Every curve fit the prediction with extraordinary precision, and every single measurement, from the frequency of the chirp to the rate of energy loss to the final mass of the merged remnant, described the surface. Not one data point touched the inside. Cecilia Cirenti and Luciano Rezzolla were not willing to let that silence persist. Cirenti, a mathematical physicist at the Federal University of the ABC region in Santo André, Brazil, had spent years studying the perturbative response of compact objects, the way these objects vibrate when disturbed. Rezzolla, a relativist at the Frankfurt Institute for Advanced Studies in Germany, had built a career modeling extreme gravitational systems. 9 years before the first detection, the pair had published a prediction. Gravitational waves, Cirenti and Rezzolla argued, would be the tool capable of breaking the deadlock between the two objects. The reason was precise. When two compact objects merge, the merged remnant vibrates. The vibration produces a characteristic signal called the ring-down, a fading oscillation whose frequency and decay rate are determined by the mass, spin, and internal structure of the merged object. For classical collapsed objects, the ring-down frequencies are predicted exactly by general relativity. For Gravastars, the frequencies depend on the properties of the stiff crust, the equation of state inside the frozen layer, and the thickness of the shell. The two sets of predictions are different. Measure the ring down with enough precision, and the interior reveals which object is real. Now, the tool had arrived. Within months of the first detection, Cirenti and Rezzolla published a direct comparison. The pair modeled the ring-down signal for a rotating Gravastar, computing the quasi-normal mode frequencies, the characteristic pitches at which a disturbed Gravastar would vibrate as the vibrations fade. Quasi-normal modes are the gravitational equivalent of how a bell rings, at a pitch determined by the shape, size, and material of that bell. Strike a bell, and the pitch tells you what the bell is made of. Strike a merged compact object, and the ring-down frequencies tell you what the interior contains. Cirenti and Rezzolla computed the frequencies for a variety of Gravastar models, then compared the results to the ringing that LIGO had actually recorded from GW1500914. The frequencies occupied different regions of parameter space. For every specific Gravastar model tested, the predicted ring-down did not match the observed signal. The ringing matched the prediction for a classical collapsed object, not the frozen bubble, not the de Sitter core surrounded by the stiff crust. The ring-down favored the pit. That result should have ended the conversation. A definitive test had been proposed. The data had arrived, the test had been conducted, and the Gravastar had failed. But the case was not closed. Cirenti and Rezzolla, to their credit as careful scientists, acknowledged a critical limitation in the same publication. Every frequency prediction hinged on the assumed properties of the stiff crust. The Gravastar configurations tested had particular internal structures, particular equations of state inside the frozen shell, particular shell thicknesses. Change the equation of state. Allow anisotropic pressure, where the pressure exerted in different directions inside the shell is not equal. adjust the thickness of the crust, or modify the compactness parameter by even a small amount, and the vibration frequencies shift. Possible Gravastar interiors occupy a vast parameter space, spanning multiple free dimensions: mass, inner radius, outer radius, shell thickness, angular momentum, equation of state. One observation rules out one configuration, but one observation does not rule out a family of alternatives that populates an entire range of possible interiors. Girenti and Mottola stated the limitation without equivocation. With every additional gravitational wave detection, the range of plausible Gravastar configurations narrows further. No detection so far has reduced the range to zero, a blow to the Gravastar, not a kill. And the reason the blow fell short reveals an uncomfortable truth about this contest. Gravastars are not a single prediction. Gravastars are a framework. By contrast, the standard collapsed object has exactly one interior for a given mass and spin. The Kerr solution. Unique. The Gravastar occupies a family of interiors, parameterized by quantities that nobody has measured and nobody can measure with current technology. Ruling out one member of the family does not rule out the family. Eliminating the entire family requires either testing every member, an impossible task, or identifying a universal feature that all members share and then demonstrating that the feature is absent. Girenti and Mottola searched for a universal feature. Instead, the pair found that the features depend on specifics of the shell. Those specifics are unknown, and so the deadlock survived the first direct test, bruised but intact, because the question was never simply whether this particular Gravastar matches the data. The question was whether any Gravastar matches the data, and that question remains open. Then the evidence took a turn that nobody anticipated. Jahad Abedi, a physicist working between the Sharif University of Technology in Tehran, Iran, and the Perimeter Institute for Theoretical Physics in Waterloo, Canada, did something that hundreds of trained analysts had not attempted. Abedi reopened LIGO data that the entire collaboration had already processed, certified, and cleared. Abedi was not looking for the main signal. The chirp, the inspiral, the merger, those phases had been analyzed to extraordinary precision. Abedi was looking for what comes after. When two massive objects merge and the merged remnant settles into a stable configuration, general relativity predicts a clean ring down, a set of fading oscillations that decay exponentially and die to silence. That prediction assumes the merger product has a true horizon, a boundary that absorbs gravitational radiation completely and reflects nothing back, absorb all energy, reflect nothing, and fall into permanent silence after the ring fades. But if the horizon is not a true horizon, if a quantum structure exists at the Planck length, above where the classical boundary should sit, then a remarkable consequence follows. Gravitational waves do not vanish into the interior. Instead, the waves hit the quantum boundary and reflect inward. Reflected energy bounces off the inner potential barrier, the angular momentum barrier at the light ring, and returns to the exterior. Faint, repeating pulses arrive at precise intervals, determined by the light crossing time of the object, the time a photon would need to travel from the quantum boundary to the photon sphere and back. Gravitational wave echoes, phantoms of the original signal returning from a wall that should not exist. Abedi and two collaborators, Anna Dikar and Nyayesh Afshordi, both at Canadian institutions, searched the aftermath of the first three LIGO detections. GW150-0914, the historic first. GW151-226, a lighter merger detected 3 months later. And a third, marginal event designated LVT-151012, too faint to qualify for the full catalogue, but still carrying a recognizable signal buried in the noise. All three physicists searched for repeating pulses at intervals set by a specific formula, 8 times the mass of the object, multiplied by the natural logarithm of the mass with corrections for angular momentum, all measured in Planck units. That formula corresponds to the round-trip travel time for a gravitational wave bouncing between the quantum wall and the photon sphere. A prediction derived from the physics of near-horizon quantum corrections. If the horizon is replaced by a reflective boundary at the Planck length, the echo delay matches that formula exactly. The prediction is sharp. The prediction is testable. And Abadi tested the prediction against the real data. The result was electric. Faint repeating pulses appeared in the post-merger data, not in one event, in all three. Combined statistical significance. After accounting for the look elsewhere effect, the penalty applied when searching across a range of possible echo templates and time delays reached 2.5 standard deviations. In particle physics, the field that discovered the Higgs boson, 5 standard deviations, is the threshold for claiming a discovery. Gravitational wave astronomy sets the bar at 3. 2.5 falls below both thresholds. Not proof, but not noise either. A signal of that strength arises by pure chance roughly 1% of the time. One trial in 100. The pulses appeared at the predicted intervals, following the predicted waveform template, in 3 independent merger events recorded by detectors separated by thousands of kilometers. Too faint to confirm. Too consistent to dismiss. The pulses sat in exactly the space where evidence goes to die, strong enough to demand attention, weak enough to deny certainty. Community response was immediate and sharp. A rival analysis conducted by researchers affiliated with the LIGO scientific collaboration appeared on the preprint server within weeks. Accusations of statistical overreach filled the rebuttal. The rival team argued that the echo template was too flexible, that the look elsewhere correction had been improperly applied, and the claim's significance was inflated by choices in the analysis pipeline. None of this was private. Every accusation was posted on the open preprint server, RxIve, visible to every physicist on the planet. Normally, disputes at this level unfold slowly, through journal submissions and conference presentations. But the echo dispute played out in real time, paper by paper, rebuttal by rebuttal, in full public view. Abadi and Afshordi fired back with a detailed response, addressing every point raised in the rebuttal. An extended appendix carried the title, The Holiday Edition, a reference to the timing of the exchange over the winter holidays and a pointed acknowledgement of the combative tone. Point by point, the appendix dismantled each statistical objection, challenged the rival analysis on methodological grounds, and defended the original significance estimate with additional cross-checks. Neither side conceded. Neither side could prove the other wrong. Suspended between 2 readings of the same data, each technically defensible, the dispute remained unresolved. The Holiday Edition became infamous in the gravitational wave community, a symbol of how deeply the echo claim had fractured the field. Some researchers treated the original result as a statistical fluctuation, one that would evaporate with more data. Others saw the first whisper of post-horizon physics, the kind of signal that history would vindicate once detectors improved. Emotional temperature exceeded what the statistical confidence warranted. 2.5 standard deviations should not provoke a public feud. But 2.5 standard deviations in favor of the horizon not existing is no ordinary fluctuation. If confirmed, the implication would overturn the most celebrated objects in modern astrophysics. Stakes transformed a marginal signal into a battlefield. Significance has not improved substantially since the original claim. Additional LIGO observing runs produced dozens more merger events, and some independent analyses found marginal evidence for echoes, while others did not. At the root of the stalemate sits detector sensitivity. Current instruments are not sensitive enough to resolve the faint, delayed pulses at a confidence level that would force consensus. Echo templates are simple, a repeating pattern at a fixed delay, but signal-to-noise ratios in the ring-down phase are low. Echoes, if real, are orders of magnitude fainter than the primary signal. Statistical weight accumulates slowly, but the pile changes nothing. Not a single gravitational wave event, recorded since 2015, has pushed combined confidence above 3 standard deviations, and not a single event has pushed below 2 standard deviations either. The evidence sits exactly in the gap between suggestive and conclusive. Nearly a decade, and the gap has persisted. Stubbornly, the gap refuses to close. Next-generation detectors, including the planned Einstein telescope in Europe and Cosmic Explorer in the United States, promise sensitivity improvements of a factor of 10 or more in the ring-down frequency band. Those instruments, if funded, if built, if operational by the middle of the 2030s, might finally push echo significance above the discovery threshold, or bury the signal beneath the noise floor permanently. But the present generation of detectors cannot do the job. Present instruments can only add thin statistical layers to an accumulating pile, a pile that grows slowly, that trends in no definitive direction, and that mocks the urgency of the question the pile is supposed to answer. Gravitational physics faces an uncomfortable hostage situation, the most consequential question in the field, the question of what occupies the interior of every collapsed star in the cosmos, is trapped behind the sensitivity curve of instruments designed to detect mergers, not to probe what mergers leave behind. A tool that opened the door to gravitational wave astronomy is too blunt to settle the dispute that gravitational wave astronomy revealed. While the echo debate burned through the preprint server, a completely separate line of evidence arrived from a direction nobody had predicted. On May 21, 2019, the LIGO and Virgo detectors recorded a gravitational wave signal that carried a new designation, GW1 900521. The signal was unusual from the start. The merger was brief, the signal was short, and the estimated masses of the two merging objects were startling. Approximately 85 solar masses for the heavier component, approximately 66 solar masses for the lighter component. At roughly 85 solar masses, the heavier object sat squarely inside a mass range that stellar astrophysics says should be physically empty. That range carries a technical name, the pair instability mass gap. Between roughly 52 and 133 solar masses, standard models of stellar evolution predict that no collapsed remnant can form through normal channels. The reason reaches back to nuclear physics. Stars in that mass range, during the final stages of nuclear burning, develop cores hot enough to produce pairs of electrons and positrons from energetic photons. Energy stolen by pair production robs the star of radiation pressure, the force that holds the star against gravitational collapse. For the most massive stars in this range, the instability does not merely trigger a supernova. The instability triggers a thermonuclear explosion so violent that the entire star is destroyed. Nothing survives. Not a remnant, not a core, not a single collapsed object. The explosion, called a pair instability supernova, obliterates everything. Forbidden, because the physics of pair production destroys the star before any collapse can complete. Yet GW1900521 showed an object firmly inside the forbidden zone. Standard explanations require a hierarchical merger scenario. 4 collapsed objects, each safely below the lower boundary of the mass gap, merge in 2 separate stages. First, 2 pairs merge to create 2 intermediate mass objects. Then those 2 intermediates merge in a second collision. The final product lands inside the gap, but no individual progenitor was ever born inside the gap. Mathematically, the scenario works. Physically, the scenario is allowed, but the demands are extreme. 4 massive collapsed objects coexisting in the same dense stellar environment, merging in 2 stages within a reasonable time frame, and no strong observational precedent exists for such a configuration. Ioannis Antonio at the University of Ioannina in Greece examined the detection through a different lens entirely. Gravastars have no mass restriction. Pair instability is only a constraint for objects that form through the standard collapse pathway, where nuclear physics dictates which stars produce remnants and which do not. A gravastar forms through a quantum phase transition at the Schwarzschild radius, not through nuclear burning and iron core collapse. That quantum transition has no mass ceiling. Pair instability, the nuclear physics process that rips apart the most massive stars before collapse can complete, is irrelevant to the formation mechanism. Remove the standard formation pathway, and the forbidden zone vanishes. An 85 solar mass Gravastar is not anomalous, entirely ordinary, just another frozen bubble around another pocket of repulsive energy with no mass restriction to violate. Both sides claim the detection as supporting evidence. Proponents of the standard framework pointed to the hierarchical merger scenario as a viable, if complex, explanation that preserves the existing understanding. Unusual conditions are required, but no known physics is violated. Dense stellar clusters, such as globular clusters or the nuclear star clusters at the centers of galaxies, provide environments where four massive, collapsed objects could plausibly coexist within a small volume. Unlikely, but not impossible. Proponents of the Gravastar interpretation pointed to elegance, an alternative that eliminates the problem entirely rather than solving the problem with a multi-stage workaround. Antonius' analysis, the Gravastar camp argued, demonstrated a point broader than a single detection. If Gravastars form through quantum phase transitions rather than nuclear collapse, then the entire pair instability mass gap is a prediction that applies only to one class of object. Every future detection of a mass inside the gap becomes a test. Find enough objects in the forbidden zone, and the standard explanation requires increasingly elaborate formation scenarios. Find objects in the forbidden zone routinely, and the simplest interpretation is that the forbidden zone was never forbidden for the objects in question. Neither side was wrong about the physics. Both explanations are consistent with gravitational wave data from GW1 9005-1, and both explanations demonstrate the same maddening pattern, the pattern that has defined this debate since the beginning. Every piece of evidence that should distinguish the two objects arrives clothed in ambiguity, carrying enough weight to keep both answers alive, never enough to kill either one. Not accidental, structural. By mathematical construction, the two objects are identical on the outside. Any measurement that probes only the exterior will return identical answers for both. The only measurements that can distinguish the two probe the interior, and the interior is protected by the most extreme gravitational environment in the universe. Breaking through that barrier requires either catching a signal from the interior leaking out, like an echo, or catching the object in a configuration where the interior matters, like the mass gap. Both signals have arrived. Neither signal was clean enough to decide. Walls are closing. Echo signals persist at a confidence level that refuses to rise above the threshold and refuses to fall below the noise floor. Ring-down tests exclude specific Gravastar models but cannot eliminate the family. Mass gap detections fit both explanations with different levels of mechanical complexity. Every instrument, every detector, every analysis pipeline is measuring the exterior of these objects with extraordinary precision and delivering silence about the interior. Evidence is not absent. Evidence is trapped in a statistical corridor where the numbers are too consistent to be coincidence and too weak to be proof. Each new detection adds another measurement to a pattern that refuses to resolve. Nearly a decade of silence. More data points will join the pile. But no observing run with the instruments that exist today will break the silence. And the resolution might require confronting a possibility that nobody anticipated, because a physicist has proposed that the inside of these objects is stranger than either side imagined, deeper than either model predicted, and more consequential than anyone bargained for. And the physicist who proposed the stranger interior was not an outsider. Luciano Rezzolla, the same relativist who had published the test designed to destroy the Gravastar 9 years earlier, returned to the problem from an office in Frankfurt, Germany. Rezzolla had spent years modeling the ring-down, the fading vibrations that a disturbed compact object produces after a collision. The ring-down test was supposed to be the kill shot. Rezzolla had designed the bullet. Once fired, the bullet failed to land a decisive blow. And the target had survived because the parameter space was too vast for a single observation to close. Now Rezzolla turned to a question that nobody in the field had considered seriously. What happens when you put one Gravastar inside another? The question sounds absurd. Nesting one star inside another would immediately destroy the equilibrium of both. Ordinary matter attracts more ordinary matter. Add a second star inside the first, and the gravitational field doubles. The inner star collapses, and the combined system rips apart. But the Gravastar is not ordinary matter. The interior pushes outward against the shell, and the shell, made of the stiffest material permitted by physics, pushes inward against the core. two opposing forces balanced in equilibrium. A repulsive core pressing against a stiff crust, and the crust pressing back against the core, and neither giving ground. If each gravestar is already stable on the basis of that balance, then nesting a second gravestar inside the first should not destroy the equilibrium. The repulsive core of the inner object pushes outward. Against that push, the stiff shell of the inner object resists. The repulsive core of the outer object pushes outward in exactly the same way. Surrounding that core, an independent stiff shell resists with equal and opposite force, holding the boundary in place. Two independent equilibria layered inside one another like a set of Russian matryoshka dolls, each one self-contained, each one exerting forces that cancel within the boundaries of the doll, leaving the next layer undisturbed. Ryzola brought a graduate student into the project. Daniel Jampolsky, working at the same institute in Frankfurt, took the equations and began testing whether the intuition could survive contact with the mathematics. The collaboration was not a casual partnership. Ryzola had built a career on the dynamics of extreme gravitational systems. Jampolsky brought fresh eyes to a problem that veterans of the field, having long assumed the object was either trivial or impossible, had stopped examining carefully. Together, the pair set out to construct the first rigorous nested gravestar solution. The mathematics did not cooperate at first. The original Mazur and Mottola model, the elegant thin shell version with isotropic pressure, the model that had launched the entire Gravastar debate in 2001, could not support nesting. Ryzola and Jampolsky proved a no-go theorem, a mathematical demonstration that a specific construction is impossible under the stated assumptions. Take two thin-shell Gravastars, the kind that Mazur and Mottola originally proposed, and try to place one inside the other. The continuity conditions of the interfaces, the mathematical rules that Werner Israel developed in 1966, demanding smooth geometry across each boundary, force the second de Sitter shell between the two crusts to collapse to zero thickness. The buffer of repulsive energy between the inner crust and the outer crust vanishes. No space remains for the second core, and the two matter shells merge into one. The nested structure collapses back to a single, ordinary gravestar, exactly the object that already existed. The beautiful simplicity of the original model, the infinitely thin shell, the maximally stiff crust, the elegant three-region structure turned out to be exactly the property that blocked nesting. The simplest version of the frozen bubble could not contain a copy of the frozen bubble. Ryzola already knew a path around the impossibility. Emil Mottola, one of the two physicists who had proposed the gravestar at Los Alamos National Laboratory, had discussed the nesting question privately with Ryzola before the formal publication. Mottola had independently arrived at the same dead end. The thin shell model was too constrained, too rigid, too perfect in a way that left no room for internal complexity. But a different kind of shell dissolved the impossibility entirely. Switch from isotropic pressure, where the force pushes equally in every direction inside the crust, to anisotropic pressure, where the forces along different directions inside the shell are unequal. The pressure pushing radially inward is different from the pressure pushing sideways, tangentially, within the curved surface of the crust. Anisotropic pressure shells have been studied for decades in the context of compact objects. Catton and Visser recognized early on that any realistic gravestar with a finite thickness shell must have anisotropic pressure. The mathematics is more complex, the equations of state are more involved, but anisotropic pressure removes the constraint that crushed the second de Sitter core to nothing. With anisotropic shells, the construction works. The inner Gravastar sits at the center, a de Sitter core surrounded by the first anisotropic matter shell. Outside the first shell, a second region of de Sitter spacetime, a buffer zone filled with repulsive energy. Then the second anisotropic matter shell. And outside the second shell, the Schwarzschild exterior, identical to the geometry around a classical collapsed object. 5 distinct regions of spacetime. 2 frozen bubbles nested inside each other, 1 compact object. And the entire system satisfies the Einstein field equations exactly. Every metric function is continuous, and every fluid variable connects smoothly across every boundary. no discontinuity anywhere in the geometry. The space-time is as well behaved at the inner interface as at the outer one. No mathematical trick, no approximation, and no hidden assumption buried in the derivation. An exact solution to the Einstein equations. The object received a name in the publication: Nestar, short for nested Gravastar, clinical, almost playful, for an object carrying implications that should unsettle anyone who has followed this debate from the very beginning. Because the nesting does not stop at 2, Mottola and Jampolsky demonstrated that the prescription for building a Nestar from 2 Gravastars extends to 3, then to 4. The recursive relations, the mathematical formulas that connect each layer to the next, follow a pattern that repeats without limit. Every additional Gravastar introduces 2 more regions, one de Sitter core and one anisotropic matter shell, and the geometry remains smooth everywhere. No singularity at the center of the innermost layer. No horizon at any boundary between layers. Layers of frozen shells racked around layers of repulsive energy, all the way down, all the way to the center, until the innermost core shrinks to a point like de Sitter mini-universe, an infinitesimal pocket of dark energy, occupying the exact location where the singularity was supposed to be. Where the classical model demands a point of infinite density, the Nestar places a point-like whisper of repulsive energy and continues without breaking a single equation. Consider what the construction means for the broader debate between the 2 objects that have been indistinguishable from the outside since the beginning. The original Gravastar was a single shell wrapped around a single core. Opponents attacked the formation mechanism, attacked the thin shell assumption, attacked the requirement that a quantum phase transition halts the collapse at exactly the right radius, with exactly the right properties. Every attack targeted the fragility of a single layer structure. Now the structure has unlimited depth. The parameter space, already vast for a single Gravastar, expands into dimensions that no finite set of observations can exhaust. Mass and thickness of each shell, energy density of each de Sitter core and equation of state inside each anisotropic layer, the angle between the radial pressure and the tangential pressure in every crust. Every layer introduces new free parameters, and the family of possible Nestars populates a mathematical space so enormous that ruling out all members requires either infinite observations or a proof that the construction cannot exist in nature. Nobody has produced that proof. The construction satisfies the weak energy condition, which demands that the energy density measured by any observer is never negative. The construction satisfies the dominant energy condition, which demands that the flow of energy never exceeds the speed of light. No exotic matter required, and no violations of causality. No wormholes, no naked singularities, and the compactness of the Nestar, the ratio of mass to outer radius, can approach the Schwarzschild limit arbitrarily closely without ever producing a true event horizon. One configuration discovered by Mottola and Jampolsky deserves special attention. In the limit where the outer de Sitter shell and the outer matter shell both shrink to infinitesimal thickness and the inner matter shell expands to fill the entire interior, a remarkable object emerges. The compactness reaches the maximum allowed value, just barely below the threshold for a classical collapsed object. But the interior is not vacuum, nor is the interior empty space falling forever toward a point of infinite density. Instead, the interior is filled entirely with matter that satisfies the standard energy conditions, matter that exerts real pressure and carries real energy density, matter that occupies the full volume from the surface inward with only a point, like de Sitter core at the very center, replacing the singularity with a regular mathematical point. A singularity-free, horizon-free, matter-filled compact object with the same external gravity as the object that every textbook says should be there. Where the standard model demands the most violent mathematical failure in all of physics, the Nestar places an infinitesimal pocket of dark energy and moves on. Then the second revelation arrived, from a direction nobody in the Gravastar debate had anticipated. The revelation had nothing to do with nesting. The revelation came from a group at the University of Hawaii at Manoa on the island of Oahu, and the claim was this: the objects are not sitting still. Kevin Croker, a physicist in the Department of Physics and Astronomy, working with Kainalu Nishimura and Duncan Farrar, an astronomer at the Institute for Astronomy, asked a question that the entire debate had been sidestepping since Mazur and Mottola published the original proposal. If the interior of a collapsed star is filled with repulsive energy, how does that energy interact with the expansion of the cosmos? Every photon traveling through the expanding universe loses energy. Wavelength stretches as space expands. A photon emitted billions of years ago arrives at Earth today carrying less energy than at the moment of emission. Red light shifts to infrared. Visible light shifts to microwave. The cosmic microwave background, the oldest light in the observable universe, started as searing hot radiation and arrived today as a faint glow, barely above absolute zero. The phenomenon is called cosmological redshift, and the phenomenon is one of the foundational observations of modern cosmology. Redshift happens because photons have positive pressure, extraordinarily small but positive, and the expansion of the universe drains energy from anything with positive pressure. Space stretches, and the photon stretches along with space, losing energy as the wavelength grows. Croker and collaborators turned the logic inside out. The reasoning was deceptively simple. A photon has positive pressure, and the expansion causes the photon to lose energy. The effect is universal. Every photon in the cosmos experiences the drain. No photon is exempt. Now consider the opposite case. What happens to an object whose interior has negative pressure? Not slightly negative, maximally negative. Pressure equal to the negative of the energy density. The defining equation of state for dark energy, the same equation of state that sits at the core of every Gravastar. The expansion of the universe drains energy from objects with positive pressure. From objects with negative pressure, the expansion draws out the opposite response, adding energy rather than draining energy away. The object gains mass steadily and without any external cause, not by absorbing material from the surroundings or merging with another object, and not through any act of accreting gas or swallowing stars, simply by existing inside an expanding universe while carrying a repulsive energy interior. The mass grows as space stretches, the exact mirror image of the photon redshift. Where a photon loses energy crossing the expanding cosmos, a dark energy object gains energy. Cosmological blue shift, an effect that follows directly from the equations of Friedman cosmology, the same equations that describe the expansion of the universe, applied without modification to an object whose interior pressure is negative. Croker and collaborators gave the broader class of these objects a name: generic objects of dark energy, GEODEs. The Gravastar proposed by Mazur and Mottola is one specific example. Any compact object with a dark energy interior qualifies, and the mass growth formula is precise. The mass of a GEOD scales as the cube of the cosmic scale factor, the single number that tracks how much the universe has expanded since the moment the object formed. An object created when the universe was 1/4 of the current size would have grown in mass by a factor of 64. An object formed when the universe was 1/10 of the current size would have grown by a factor of 1,000. Numbers that transform the demographics of compact objects across cosmic time. A 1.5 solar mass remnant, the typical product of a massive star dying in the Milky Way, produced at a redshift of 2 when the universe was roughly 1/3 of the current size, would reach approximately 40 solar masses by today, without swallowing a single particle, without merging with another object. All of this mass growth arising from nothing beyond the passive coupling between the interior pressure and the stretching of space. The implications struck directly at the mass gap debate, the unresolved tension that had been building since the third act. GW1 900521 showed an object at 85 solar masses, squarely inside the range that stellar physics says should be permanently empty. The standard explanation demanded a hierarchical merger scenario, 4 collapsed objects merging in 2 stages within a dense stellar cluster, a configuration with no observational precedent. Croker and collaborators offered a completely different path. A 3 solar mass remnant, born at a redshift of 2 from a perfectly ordinary massive star, undergoing a perfectly ordinary core collapse supernova, would grow through cosmological blue shift alone into the forbidden mass range. No hierarchical merger and no dense stellar cluster required. Zero exotic formation channels, zero fine-tuned initial conditions. The forbidden zone was only forbidden if the objects had classical interiors that did not couple to the expansion. GEE interiors dissolve the boundary entirely, because the boundary was never a boundary for the objects. The boundary was a boundary for the formation channel. Remove the formation channel, replace the classical interior with a dark energy core, and the mass gap vanishes. Then the mass function test landed, and the result was striking. Croker, Nishimura, and Farah took the standard Salpeter distribution, the time-tested model describing how many stars of each mass form in a given stellar population, and evolved the resulting remnant population forward through cosmic history. One model treated the remnants as classical collapsed objects. Mass stays fixed. No growth. The other model treated the remnants as GEODs, coupling the mass to the cosmic expansion through the blue shift formula. Both models started from the same initial population and used the same star formation history. The only difference was the interior. Classical remnants, evolving without mass growth, produced a mass distribution that sat in tension, with the observations recorded in the first LIGO gravitational wave transient catalog at more than 2 standard deviations. The predicted masses were too low. Merger rates in the predicted range did not match observations. The overall shape of the distribution did not fit the data. Forcing a fit required invoking low metallicity stellar environments, exotic formation channels, abnormally massive progenitor stars, or primordial object formation at extreme rates. None of those additions were included in the baseline model. The GE-ORD mass distribution told a different story. Evolved with cosmological blue shift from the same initial Salpeter population, the GE-ORDE ODI model matched the LIGO observations within half a standard deviation. Agreement at less than half sigma, using solar metallicity progenitors, the ordinary stars that populate the ordinary disk of the Milky Way. Remnants in the 1.1 to 1.8 solar mass range at birth. Remnants that grew passively across billions of years of cosmic expansion. Arriving at the merger masses LIGO had been recording since 2015 without invoking a single exotic ingredient. 2 standard deviations of tension for the classical model, less than half a standard deviation for the GEOD model. The agreement was not engineered. Instead, the agreement followed from one assumption: the interior contains repulsive energy, and that energy couples to the expansion of the cosmos. One assumption, one formula, a single prediction that matched the data more cleanly than the model that had been treated as the default for decades. Dead stars and the dominant force reshaping the cosmos share a link that is not figurative. That link is mathematical, encoded in the field equations. Repulsive force, contained within every frozen shell, is the identical force driving galaxies apart right now. Dead stars feeding on the expansion of the cosmos. And cosmological coupling runs in both directions. If enough collapsed remnants across the observable universe contain dark energy interiors, the total energy contribution of those objects to the cosmic budget grows as the universe expands. More energy, more expansion. Greater numbers of massive stars die and produce additional remnants. Those remnants grow as the expansion accelerates. A feedback loop without a ceiling, without a natural stopping point, without any mechanism in the known laws of physics that would apply the brakes. The darkest objects in the cosmos and the force dismantling the large-scale structure of the universe are not separate phenomena observed at different scales. Both are the same phenomenon, coupled through the interior of every collapsed star, linked by a mathematical identity that general relativity has contained since 1915, but that nobody connected to the Gravastar problem until Croker's group published the mass function analysis. The alternative was supposed to be simpler: a bubble of repulsive energy, wrapped in a frozen shell, instead of a bottomless pit descending toward infinite density. An object that required no broken physics and no lost information. An object that preserves information instead of destroying information, simple, clean, and elegant. Instead, the alternative has turned out to be deeper than anyone bargained for. The frozen bubbles can contain copies of themselves, nested layers stretching down to an infinitesimal point of repulsive energy, at the center where the singularity was supposed to be. Rather than passive remnants sitting quietly inside the expanding cosmos, the objects are active participants in the expansion, gaining mass as the universe ages, feeding on the stretching of space, contributing to the very force that stretches space further. The parameter space is not shrinking under the pressure of new observations. Instead, the parameter space is expanding, populated by an infinite family of nested configurations that no finite experiment can exhaust, and supported by a mass function that matches the merger data more cleanly than the standard model. And that expansion of possibility creates a trap far worse than the one the evidence built in the previous act. Because if the alternative is this strange, this consequential, this deeply woven into the fabric of the expanding cosmos, then the question changes. The question is no longer whether the alternative matches the data. The question is why, after 25 years, nobody has been able to prove the alternative right, or prove the alternative wrong. And the answer to that question is the most uncomfortable part of the entire debate. Nobody can explain how the shell forms, not the physicists who proposed the object, nor the theorists who extended the mathematics to nested configurations and cosmological coupling. In 25 years of published work, not a single calculation has ever shown a collapsing star stopping. Every Gravastar paper begins with the finished object already sitting in place, stable, cold, dark, and mathematically perfect. The question of how that object came to exist is never answered. The question is acknowledged, placed carefully on the table, and then the paper moves on to other matters. Formation is the wound that will not close, and the critics have aimed at that wound relentlessly since the day the proposal landed on the preprint server. The objection targets the equivalence principle. A freely falling observer crossing the Schwarzschild radius feels nothing unusual, no jolt, no resistance, and the principle demands that smoothness. Any phase transition at that location, any quantum intervention that reorganizes the vacuum to produce a stiff crust, would violate that demand by creating a measurable difference between a freely falling frame near the collapsing star and one drifting in empty space. The Gravastar requires exactly that violation, a measurable physical event at a location where the deepest principle in gravity forbids physical events. Mottola had anticipated the attack from the beginning. The equivalence principle is a statement about local physics. Quantum fields, responding to the global geometry of the space-time, might behave differently. Photon energies climbing toward the Planck scale near the Schwarzschild radius push into a domain where the classical principle might not survive. The rebuttal is sophisticated but incomplete. Nobody has derived from first principles the mechanism by which the quantum vacuum reorganizes during collapse. The transition requires the entire vacuum to shift state at the precise moment when the collapsing surface approaches the critical radius. That precision is troubling. A transition demanding exquisite timing must explain why the timing works. The explanation has not arrived. Consider the scale of what the proposal demands. A star, 15 times the mass of the Sun, exhausts the nuclear fuel in the core and begins collapsing. The collapse accelerates. Within seconds, the core contracts from the size of the Earth to a sphere roughly 20 kilometers across. At that moment, according to Mazur and Mottola, the quantum vacuum must recognize the approach of the critical radius, undergo a phase transition analogous to water freezing into ice, and produce a shell of the stiffest material in the universe, all before the collapse overshoots the boundary. The window for the transition is extraordinarily narrow. The speed of the collapse is a significant fraction of the speed of light, and the physics governing the transition, quantum gravity at the Planck scale, belongs to a domain where no complete theory exists. Formation requires a quantum gravitational process, intervening with surgical precision during one of the most violent events in the cosmos. The demand is extraordinary, and without the explanation, the Gravastar remains a valid endpoint, but not a demonstrated pathway. A destination with no road leading to the destination. and no one who witnessed the construction along the way. Elegant blueprints, sound foundations, but no tool marks remain, and nobody can explain how the building got there. In 2016, Mottola presented the formation argument at a workshop in Perimeter Institute, standing before a room of relativists who had spent careers on the standard model. The question from the audience was blunt. If the transition cannot be derived from first principles, why should anyone believe the endpoint exists? Mottola pointed to the ultraviolet catastrophe. In 1900, classical physics predicted infinite radiation energy at short wavelengths, a result that was clearly wrong. Nobody could derive the correct formula from first principles until Planck introduced quantization. The correct endpoint existed before the derivation. Nature does not wait for theorists to catch up. The room went quiet. Not because the argument was conclusive, but because the argument was uncomfortably familiar. Every physicist in that room had been trained on the same story. The story of how quantum mechanics was born from an endpoint, a mathematical result that nobody could derive from first principles until the derivation arrived decades later. The parallel was too close to dismiss and too imprecise to confirm. The formation problem survived the exchange, but the wound stayed open. Chiarenti and Resola delivered the strongest empirical blow. The ringdown from GW150914, the vibration frequency of the merged remnant, matched the prediction for a classical collapsed object, not for a gravastar. The frequencies occupied different regions of parameter space. For every specific model Chiarenti and Resola tested, the measured signal rejected the Gravastar alternative. The rejection was published quickly, clearly, and without hedging. A decade of anticipation had built toward exactly that moment. Chiarenti and Resola had designed the bullet, the detection delivered the target, and the result favored the pit. But the blow did not land cleanly enough to end the fight. The models Chiarenti and Resola tested assumed specific shell properties, specific equations of state, specific internal pressures, changed the equation of state inside the frozen layer. Allow anisotropic pressure, where radial and tangential stresses inside the shell are unequal. Adjust the compactness by even a small increment, and the vibration frequencies shift. Defenders face a target that moves with every publication. Each new model adds free parameters. Each parameter shifts the predictions, and the family of possible interiors grows faster than the observations can constrain the family. Chiarenti and Resola acknowledged this limitation directly in the same publication. The blow left a wound, but did not reach the heart, and the family of possible interiors survived, bruised but intact, populating a mathematical space that no finite number of observations can exhaust. Maddening asymmetry defines this contest. Once mass and spin are fixed, the standard prediction narrows to a single allowed interior. The Kerr solution, unique and complete. One prediction, one target, and a direct test. The Gravastar offers an entire spectrum of interiors, shaped by quantities that no current instrument can constrain. Excluding every possibility demands either exhaustive testing of each configuration or the discovery of a single universal signature shared by every Gravastar. Nobody has found that signature. The standard framework takes aim at a target that shifts with every new publication. Ammunition is finite. The target space is not. And yet the problems that created the Gravastar, the problems that drove Mazur and Mottola to propose the alternative in the first place, have not been solved by the standard framework either. The mathematical failure at the center of every classical collapsed object remains. Infinite density, zero volume, and every equation screaming that the model is broken. Every proposal to resolve the point of infinite density within the standard framework has required assumptions at least as exotic as the Gravastar. String theory proposes extra dimensions. Loop quantum gravity proposes a quantum bounce. The fuzzball conjecture replaces the interior with a tangled ball of strings. Every one of those proposals is mathematically sophisticated, and every one of them lacks a single shred of direct experimental confirmation. That failure at the center is a confession that the equations break, and the confession has stood unresolved for more than a century. Nobody has fixed the breakdown. Physicists named the breakdown, diagrammed the breakdown, and built careers around the breakdown. But the breakdown persists. The information paradox persists as well. Hawking radiation, the theoretical prediction that collapsed objects slowly evaporate, produces thermal radiation that carries no information about the matter that originally fell in. The process appears to destroy quantum information, violating the foundational principle of unitarity that underpins all of quantum mechanics. 40 years of proposals, from holographic screens to quantum error-correcting codes to the firewall conjecture, have attempted to resolve the paradox without abandoning the event horizon. None of those proposals has been tested experimentally. None of those proposals has achieved consensus, even within the theoretical community. The paradox is a symptom. The event horizon is the cause. Remove the horizon, as the Gravastar does, and the paradox dissolves. Information was never destroyed because the boundary that traps information never formed. The elaborate machinery invented to explain where information goes, the decades of conferences and thousands of papers addressed a problem that a different object makes disappear entirely. 40 years of intellectual labor directed at rescuing a principle that was never in danger if the horizon never existed. The cost of that possibility is staggering. Not because the alternative is wrong, because the alternative might be right, and nobody can tell. The entropy formula that cancels the Planck constant, the accusation Mazur and Mottola leveled, comparing the celebrated Bekenstein-Hawking result to the formula that broke physics in 1900, has never been answered. The silence around that accusation has never been broken by a definitive rebuttal. Gravastar entropy remains 20 orders of magnitude smaller, comparable to the disorder of the star that formed the object, and the standard framework has offered no explanation for why a formula that claims to be quantum contains no quantum mechanics. 3 problems remain unresolved. The breakdown at the center that shatters the equations, information lost behind a barrier that might not exist, an entropy formula that cancels the constant meant to make the formula quantum. What if the interior of a classical collapsed object is wrong? Not wrong in a minor technical detail, but wrong in the fundamental architecture of the object. Perhaps the pit is not a pit. Perhaps the barrier is not a barrier. And the celebrated surface entropy might be a mathematical coincidence, inherited from a classical framework that does not apply at the relevant scale. Gravastars were born from these wounds, and every year those wounds go unhealed. The alternative gains credibility, not because the alternative has been proven, but because the standard framework has failed consistently to fix the problems that the alternative was designed to solve. Every new gravitational wave detection lands in the same silence. In spiral confirms the masses and the spins, merger confirms the energy radiated, and the ring down confirms the exterior geometry with extraordinary precision, and the interior remains untouched. Not a single data point in any merger event recorded since 2015 has penetrated past the surface of these objects. Dozens of detections, hundreds of parameters extracted, and every single parameter describes the outside. The inside is protected by the most extreme gravitational environment in the cosmos, and the instruments designed to probe the cosmos are too blunt to reach the interior. Every detection adds another number to an accumulating record that refuses to converge, refuses to diverge, and refuses to resolve the question that justified building the detectors in the first place. The silence has lasted 25 years. Mazur and Mottola submitted the original preprint in 2001. A quarter century of peer-reviewed publications, of gravitational wave detections, of increasingly sophisticated models, of echoes and mass gaps and nested configurations and cosmological coupling. And the deadlock has not budged. Not because evidence is absent, because evidence is everywhere, arriving from every direction. But every observation lands wrapped in the same statistical fog, strong enough to sustain 2 competing interpretations, too weak to eliminate either one. The stalemate is not a failure of effort. The stalemate is architectural. 2 objects sharing the same exterior geometry will, by construction, produce the same answer for every external measurement. The deadlock is not a gap in the data. but a direct consequence of the equations themselves. Next generation instruments might change the balance. The Einstein telescope, a proposed underground detector in Europe with arms 10 kilometers long, promises sensitivity improvements a factor of 10 or more in the frequency band where ring-down signals reside. Cosmic Explorer, a proposed 40-kilometer facility in the United States, would push further still. Those instruments, if funded, if built, if operational by the middle of the 2030s, might resolve the faint harmonics in the ring-down, the higher-order quasi-normal modes that depend on the internal structure of the merged remnant. Those harmonics are the fingerprints of the interior. Measure the harmonics with enough precision, and the question of what occupies the inside finally becomes answerable. Will a detector 10 times more sensitive finally break the silence? Engineers at the European Gravitational Observatory have already begun site selection studies, drilling boreholes into candidate rock formations in Sardinia and the Netherlands, measuring seismic noise at frequencies that would overwhelm a surface detector. The goal is a triangular underground facility, 3 arms meeting at 3 vertices buried deep enough to escape the vibrations of traffic, ocean waves, and continental drift. Construction could begin before the end of the decade. But even under the most optimistic funding scenarios, the first observations would not arrive until the middle of the 2030s. The present generation of detectors cannot do the job. The detectors that proved gravitational waves exist, were never designed to probe what the collisions leave behind. That question requires a sharper instrument, and the sharper instrument does not exist yet. And somewhere in the data already collected, the answer might already be hiding. Not in the main signal, not in the chirp, or the plunge, or the ring down that every analysis pipeline has already processed and published. In the faint, delayed pulses that arrive afterward, at intervals set by the round-trip travel time of a gravitational wave bouncing between a quantum wall and the photon sphere. Pulses that obedient collaborators claim to detect at 2.5 standard deviations, too faint to confirm, too consistent to dismiss, buried in noise that the current instruments cannot separate from signal, in data that has already been collected, stored, and waiting for a detector sensitive enough to settle the question. No new physics is required, and no new theoretical breakthrough is needed, only a better ear, tuned to the frequency of the answer already buried in the noise. An instrument with the sensitivity to hear what the universe has already said, in a whisper too faint for the instruments that exist today. The most iconic objects in physics, the ones printed on t-shirts and painted on murals and featured on the covers of magazines, might be placeholders. Placeholders for an object that is the opposite of a whole. An object with no pit at the center, no barrier at the boundary, and no broken physics anywhere inside. An object filled with the same repulsive force, the very force that is pulling every galaxy away from every other galaxy, right now, at this moment. The discomfort that realization produces is not a failure of understanding. The discomfort is the honest shape of the frontier. Every generation inherits objects that cannot be fully explained and tools that cannot yet distinguish between competing realities. This generation inherited the collapsed star and the frozen bubble, 2 answers occupying the same space, both valid, both unverifiable, and the silence between them is not a gap in the data. The silence is the sound of a question that the universe has not yet answered. And every new detection, every faint ring in the aftermath of a collision billions of light years away, carries the possibility that the answer is already present, already recorded, already waiting in the data. Not for a new theory, not for a different equation, for the moment when a sharper instrument finally makes the whisper loud enough to hear. Nobody has seen the inside. That fact opened the first crack. Every challenge since has widened the fracture, until the original object and the replacement stand side by side, identical from the outside, opposite on the inside, and neither willing to disappear. No instrument ever measured the inside. Equations broke at the center, and the community named the break instead of fixing the break. A different solution emerged from the same mathematics, a frozen shell around a core of repulsive energy, and the exterior matched so precisely that no instrument could separate the two. Evidence arrived from collisions, from forbidden masses, from faint pulses in the aftermath of mergers, and every detection landed in the silence between two answers. The alternative deepened. Layers within layers, mass growing as the cosmos expands. Dead stars, coupled to the force pulling galaxies apart. And the strongest counter-evidence, the ring down that favored the pit, could not eliminate the family of alternatives, populating a parameter space too vast for any finite set of observations to exhaust. The most iconic objects in physics might be placeholders. At the center, the singularity might be a confession, not a prediction. And the barrier at the boundary might be an artifact, a product of a model that works on the outside and produces nonsense on the inside. Nobody alive can prove which interior is real. That limitation is not temporary. The limitation is structural, built into the geometry of two objects sharing the same exterior. That discomfort is not a failure of knowledge. That discomfort is the frontier. Every generation inherits objects that cannot be fully explained, measurements that cannot yet separate competing versions of reality. This generation inherited the collapsed star and the frozen bubble. Two answers occupying the same space, both valid, both beyond verification. Silence sits between the two. And that silence is not empty. The silence is where the next answer will be born. Somewhere in the cosmos right now, two compact remnants are spiraling inward. Energy from the collision will cross 1 billion light-years before reaching a waiting detector. And in the faint ringing after the collision fades, buried in the noise, the answer might already be present, already recorded, waiting for an instrument sharp enough to hear what the universe has already said. The fascinating part is not that we answered the question about gravastars and black holes. The fascinating part is that the evidence keeps pointing toward a reality far bigger and far stranger than anyone expected. We do not get closer to the truth by collecting answers. We get closer by learning which questions we have not asked yet. These videos are a labor of love, but the research and production also take a lot of late nights. I would really appreciate it if you hit that like and subscribe button. I'm incredibly grateful for everyone who has supported the channel so far, and that support is what keeps these deep dives going. But mostly, I want to know what you think. Did I miss anything about gravastars? Or do you think the gravastar model has a fatal flaw nobody has addressed? Let me know in the comments. I will catch you in the next one. Let curiosity guide you, keep learning, and know that you are always appreciated.